I went quite slowly through the last question because it was a really important question and quite hard. I'm going to hopefully start a little bit quicker this time. So, complete combustion of propane. Propane is that molecule. You may or may not remember that propane is that structure, 3 carbons and 8 hydrogens. But when you burn it, you get carbon dioxide and water. To balance this equation, we just tot up the oxygens on the right-hand side. There's 6, which is 3 times 2, add 4, which is 10. So 5 lots of 2 is 10, so that's the answer there. You just need to know the test for carbon dioxide, which is bubble 3 lime water. That's 1 mark, and you can only get the second mark if you say the first mark, but you then have to say it goes cloudy. That's that one. Complete the symbol equation for this reaction. You have to remember, and maybe you haven't learned this yet, maybe you have. If you have, you'd know that propene is C3H6, so the alkenes are all CnH2n, you might remember. So how many carbons there were, there's that many hydrogens. You could have worked it out as well. You've lost 2 hydrogens, so you must be with that. So well done if you got that one right. Many of you did. The test for hydrogen, another knowledge one. So again, this was pretty good, but lit splint gets you the mark, and squeaky pot gets you the mark. And then another chemical test, one that you're less likely to have remembered, and fewer people got this one right. But alkenes are those molecules with double carbon-carbon bonds, or carbon-carbon double bonds. And the test for anything with that chemical feature, we call a functional group, is we chuck in bromine water. And you'd have come across this when doing the cracking lesson, maybe. Bromine water, and it goes from no, that's spelled wrong. It wasn't, was it? Orange to colourless. There we go. So 1, 2, 3 marks. Easy, easy. If you know it. How is crude oil formed? Now, I thought this was really hard. I feel a bit bad for putting this in your paper, so forgive me. But this was mean. The way they marked this was really, really strict, I think, in the real paper back in 2020. And maybe you struggled to get the marks here. But I'd like you to know this if you possibly can. But you should be talking about plankton or marine animals or biomass. We'll just use plankton. So little tiny sea creatures from a very long time ago. You get a mark for mentioning plankton or biomass or marine animals from a long time ago. You should get a mark for that. What happened is they died and they sank to the bottom of the sea, and eventually, and this is the important thing you've got to say, that they got buried in mud. And the key thing really is they got compressed under that mud. You get the mark for that, but if you talk about the fact that they've been compressed and squeezed in that rock for, and then the next thing is for millions of years. I think many of you got the mark for talking about millions of years. You can't just say a long time. Oh no, you can. You get the mark for a long period of time, but millions and millions of years that took, and after those millions of years, crude oil's formed. You can imagine on enormous quantities. And how is it separated? Now this is one that I don't regret giving to you as a question, because it's one that is a pretty common question, and you should learn it if you haven't learnt it. But you might remember the process. Very briefly draw a diagram, but it's going to be a pretty ropey diagram. But you might remember a sort of chamber-looking something. Oops, and you'll draw it badly. Like this. There we go, something like that. And the crude oil is pumped in at the bottom, and you've got these different places where the different fractions come out. And the things you need to say about crude oil fraction distillation, and the first thing that you've got to say is that you heat it before putting it in. So heat it about 400 degrees. So the first mark is to say heat the crude oil, heat the mixture of hydrocarbons. Remember, crude oil is just a mixture of lots of different hydrocarbons that we're going to try and sort out. So heat the crude oil, you might remember it's something like 400, 450 degrees, something like that. And what happens then is most of the fractions, most of the alkanes and alkenes, whatever else are in there, they will evaporate. In other words, they turn into a gas. They turn into a gas. And so you're actually entering the chamber as a gas rather than as a liquid. And I think that's the one place where people are confused usually and don't really understand that they're going in as a gas rather than as a liquid. It's not quite the same as normal distillation. They're going into the chamber as a gas. And understanding that gets you 2 marks. Because they've got different boiling points, they then turn back into a liquid at different temperatures. You might remember that the chamber is relatively cool at the top and hot at the bottom. So the gas goes in, and as the gases rise through the chamber, they cool down because it's cooler at the top. And then when they get to their boiling point, which is the same as their condensation point, they turn back into a liquid. And you get the mark for saying the fractions have different boiling points. I thought that was quite a difficult wording. They were quite fussy about that. And when they get to their particular boiling point, you talk about the gases condensing. Okay, so that's the 4 marks, right? Moving on. Question 5.3, general formula for alkanes. I mentioned earlier on in my walkthrough here that that alkenes are CnH2n, but alkanes, this is just a very, very common question. You can work it out actually if you think about it from the information you've got here, but it's however many carbons there are, which we call N, there's twice as many hydrogens, add 2. So if there's 5, you times 5 by 2, you get 10, add 2, you get 12. Right, so that's the general formula for alkanes. And the boiling point, you can see that as the chain gets longer, as you get more carbons, the boiling point goes up. And believe it or not, you get a mark even for saying that. So the first mark is increase chain length, you increase boiling point. 1 mark. And this again, I told you earlier on in the walkthrough that the bonding topic is the most important topic you can spend time on because it's going to affect what you do, for example, in this topic now. And you should be knowing that these things, you should know these things are simple covalent substances, which means when you boil them, you overcome intermolecular forces between the molecules. And so it must be that the intermolecular forces are stronger for the bigger molecules because they've got higher boiling points. So intermolecular, I'm not going to write it out, forces are stronger for longer chains, molecules. Now, it's not to do with the strength of the bonds. So some of you wrote about the strength of the bonds within the molecule. Those bonds don't break. They're very strong covalent bonds. It's the forces between, those weak forces between the molecules. The bigger the molecule, the stronger those weak forces. So you'd say intermolecular forces are stronger for longer chain molecules. And so something like, and so boiling point increases. I haven't quite got it exactly as the mark scheme, which I'll just read you now. But it says the boiling point increases as the number of carbon atoms increases, which is the same as more or less that. And that's because the intermolecular forces increase in strength. And then you say for the third mark, they increase because the molecules get bigger. So let's add that as a point with increasing molecular size. And you get exactly the same answer where you talk about the boiling points of the halogens. F2, Cl2, Br2, I2, molecules get bigger and the boiling points go up for exactly the same reason. Let's finish off with 5.5. So this is a funny one, isn't it? You've probably never seen this, but you can separate, and let's just read it. This is a funny old question. I've not seen this one apart from this one time. The thing that it's asking you about really, and it's worth thinking about this when you get to, if you know the course really well and you've revised really well, you might remember the kind of syllabus points. The syllabus point is checking here is that you understand about that as you get longer carbon chains, the molecules get more viscous, thick and sticky, and they flow less freely therefore. And if you allow these fractions or these alkanes to go through this tap in this piece of kit called a separating funnel, the thick and sticky, longer chain ones will flow more slowly. Imagine like thick, sticky crude oil. You've seen that stuff that you've probably seen pictures of seagulls, unfortunately, kind of caked in it. That would be the very long chain alkanes, whereas a very short chain, fast-flowing runny alkanes like petrol are much less so. So the viscosity, the thickness changes. So it's telling you that the shortest chain alkane, C5H12, takes 6.4 seconds. What will be the trend in time? But all you've got to say is as you increase in carbon atoms, the time increases. And that's because you get an increase in viscosity with increasing chain length. You would have been taught that when doing the whole fractional distillation topic, so hopefully you'll remember that, but that's the last point I'd like to make. Hope it went well.